We're now going to look at an example of a simple MOS current mirror. So if you recall from the prior part of the lesson, if we run a reference current through a diode-connected transistor, we generate a stable bias voltage. And we're going to use that stable bias voltage to bias a second transistor that we're going to use as a current source. This could, of course, be the current source that we use in one of our amplifiers for an active load. Or we could just be using it to generate several stable currents across an IC, for instance. So in our current mirror, we have a line of symmetry along the vertical axis here, and we mirror transistor M1 here across that line of symmetry to make transistor M2. And we generate an output current, I sub 0. And of course we do this with a stable bias voltage and a reference current flowing through that transistor M1. Now this is a current source, but unlike an ideal current source, we do have to have a certain voltage across transistor M2, and in fact the voltage that we have to have across M2 needs to be greater than what we call the VD sat for the transistor. In other words, we need to make sure that M2 is always in the saturation region. So in this case, we know that this transistor M2 is acting as a current source. And as such, we're going to get an output current I0 that's equal to the reference current, Iref, if we say that the drain to source voltage of transistor 1 is equal to the drain to source voltage of transistor 2, and lambda is equal to 0. In other words, these are ideal transistors that have infinite output resistance. Now, in reality, that isn't going to be the case. Alright, so we know we can write what the currents are here. So we know that the drain current ID1 is equal to Iref. And we also know that it's equal to mu n C ox over 2 times W over L1 times V bias minus VT squared times 1 plus lambda times VDS1. And we also know that the output current, which would be the drain current for transistor 2, ID2, is equal to IO, is equal to mu n C ox over 2 times W over L 2 times VB minus VT squared times 1 plus lambda times VDS 2. So these are just the equations for transistors operating in the saturation region. Now, one of the nice things that we can do here is it can sometimes be desirable for the output current to equal the reference current, but we also might like to create an output current that's a multiple of the reference current. And in order to do so, all we would have to do is scale the W over L ratio of the transistors to achieve this. So for case 1, we would have that M1 is equal to M2. In other words, W over L1 is equal to W over L2. These are called matched transistors, and our output current is equal to the reference current. We could have a second case where M2 is a multiple of M1. In other words, we could say that W over L2 is equal to N times W over L1. And we do this simply by making transistor M2 larger than transistor M1 in the width dimension. And if we do so, we would note that our output current, I0, would equal N times the reference current. So this is a nifty way to generate multiple different currents with different amplitude levels across the chip simply by changing the ratio of the device's geometries.